So we're here today to talk about convolutional neural networks. And we discussed them a little bit in the lecture, but hopefully today we'll get a much better intuition for what they do and how they work. And we're going to start with a data set. It's called the slash data set. And I'm going to show you what it looks like. Okay, so every example is either a forward-leaning slash, which is class 1, or a backwards-leaning slash, which is class 0. And every slash is on a background of some random noise, just to make it more interesting. Now, this is actually a fairly challenging data set for many conventional machine learning models, because it's not clear what the appropriate features are for classification here. So it's not really helpful to use pixel-wise classification, because the slash can appear anywhere in the entire image. It can appear here, it can appear here, it can appear, in any part of the image. So we're going to try and train a few different machine learning models to classify this data set. And then we'll see how it works with a convolutional neural network. Okay, so I'm going to generate some samples. Now I'm generating a set of samples, and then I'm going to take the set of samples, and I'm going to make a version of them that's flat and a version of them that's not flat. What do I mean by that? Well, we know that the conventional machine learning models and the fully connected neural network just expect one long row of features for every sample, right? So in this case, the images are 30 by 30. So the flat data shape, which is going to be used for all of the machine learning models except the convolutional neural network, has 750 samples, and each sample has 900 rows, 900 columns. And that's because there are 900 pixels in each image. So every pixel is a feature, and we don't really care about their particular spatial arrangement. For a convolutional neural network, we know it does care about the spatial arrangement of the features. And here we can see the input to the convolutional network for each of the 750 rows is going to be a volume with height and width of 30 and depth of 1. So there's one color channel here because this is a black and white image. So the depth will be 1. Okay, and our feature data is in this particular range. All right, so we're going to start by training some of our conventional machine learning models. Okay, we'll try a logistic regression, a k-nearest neighbor model, a 3 nearest neighbor model. We'll look at a random forest, a linear SVM, and an SVM with an RBF kernel. Okay. Now, I'm going to go ahead and start training this, but let's see what you guys think. Which model do you think will be best at generalizing this data? So training on the test data set and then score on the, training on the training data set. Which model do you think will have the best score on the test data set for this particular data? Okay, take a few more moments to vote. All right. So here are the results of this poll. Now, I see some students said the SVM kernel would do the best. maybe because it's most complicated. Let's look back at this data and think about what every model would do with this data. So the logistic regression would try and find a coefficient that should be associated with each pixel in the image, where, let's say, a large coefficient would indicate that writing in this pixel is strongly associated with belonging to the 1 class, which is the forward-leaning slash. Or a negative coefficient means that writing in this pixel is more associated with belonging to the backwards-leaning slash. Okay. Is this a good approach for classifying this data? It's not really very helpful because the slash can be anywhere in the image. So writing in a particular pixel isn't an indication of belonging to either class. So I expect that the logistic regression won't really do well at all. Okay, what will the random forest do? Well, the random forest is an ensemble of decision trees. So each individual decision tree will make decisions, again, on single pixel values. Now, I can see that being a little helpful. You could essentially memorize the entire training set. And this can be a little more helpful than the logistic regression just because you can capture interactions. So you can say, for example, okay, if there is a pixel in this image, if there's writing in this pixel, then on the next split, check if there is writing in this pixel, and then check if there's writing in this pixel, and so on. So you can use a decision tree to kind of memorize individual test samples, but it's not really going to help you memorize the individual training samples, but it won't help you actually generalize to a test set. What about the support vector machine? So also with a linear kernel. So the support vector machine we know is kind of like a weighted nearest neighbor. It's going to try and find the test samples that are, let's say, the most difficult to classify. And it will try and then compare we'll try and find the training samples that are most difficult to classify. And then for each new test sample, it will take, let's say, the weighted sum of a kernel function of the new test sample and each of those training sample support vectors. And essentially, we'll use those to determine whether it's more similar to the positive class support vectors or more similar to the negative class support vectors. So I think that linear and RBF kernel, there's no real benefit to the RBF kernel here. You can measure similarity pretty well using either kernel. But again, I don't think either of them will be able to generalize very well because similarity between a test image and a training image, well, maybe if you get lucky, you'll have some test images that are kind of very similar to some training images, but it won't really help you generalize the concept of a forward slash or a backward slash. And the k-nearest neighbors will, of course, do something similar. It will just memorize all the training samples. So if you have a new test sample that happens to be similar to the, a training sample you already found, then great, it will do well. But if not, I wouldn't expect it to do well at all. Okay, so let's see how it did. All right, so this is a training score. All of these models were able to learn the training data pretty well, just because they're essentially memorizing the training data. Most of them do about the same as random chance on the test data. So you have a 50% chance of predicting the right answer, and most of them are right around 50%. The k-nearest neighbors looks like it does pretty well, but that's really just because it's a kind of simple data set. So if you have enough training samples, you can kind of memorize the training samples and let's say that all of your test samples will already be known to you. But if you have a smaller data set, let's try it again with a smaller data set. Right, with a smaller data set, performance goes down. If I would reduce the data set size again, it would go down even more. So none of these models really do a good job learning this data. Okay. And the reason this data set is so difficult is because we really need good feature extraction here. So the relevant feature, which is the slash, can appear anywhere in the image. And we need to be able to identify it no matter where it appears. Okay, what about a fully connected neural network? Do we think that would do well? Okay. A fully connected neural network will have the same problem as the others, exactly. So a fully connected network is still just going to look at individual pixels and try to determine whether individual pixels are associated with belonging to the positive class or the negative class. But let's give it a try anyways. I'm going to make a fully connected neural network with 64 hidden units in each of 3 hidden layers. I'm going to use a couple of new features here for training. One of these is early stopping. I don't remember if I showed you that before. But early stopping says keep an eye on the validation data. So I've indicated here that I want to save 25% of the data for validation. So 25% of the training data that I pass will be saved for validation. And I'm going to use that validation data to decide how to adapt the training process. So I've specified 2 ways of adapting the training process. So after every epoch, it computes the validation accuracy. And if there is a plateau, so the validation performance has not improved in a few epochs, here I said in, let's say, 2 epochs, then I'm going to reduce the learning rate by this factor. So you can see here, for example, the validation performance was kind of relatively similar for a while. And so we reduce the learning rate. Here we reduce the learning rate again. So if I see that I'm not improving, I might think, oh, I might kind of be stuck bouncing around somewhere. And maybe in order to descend more on the loss surface, I need a smaller learning rate. So we'll reduce the learning rate if there is a plateau for a couple of epochs. Now, if I'm kind of stuck, and even after reducing the learning rate, after 20 epochs, I'm still not improving my validation performance, then I'm just going to stop, even if I haven't reached 100 epochs. Okay, so you can see here, I stopped after only 21 iterations, 21 epochs. I was not really successful at learning much of anything here. So we'll compute the model scores. I have both the training and test performance of about 50%. Okay, so about even with random chance. All right, let's try our convolutional network. So in our convolutional network, we have a few new layers that we haven't seen before. We have some convolutional layers. So let's take a look at these. So we have convolutional layers available for 1D, 2D, or 3D data. Here we're working with the 2D data. And then for each convolutional layer, we specify how many of these filters we want. So every convolutional layer has 1 or more filters that scan the image and compute the convolution of the filter and the image. Okay. We're going to specify the kernel size. The kernel size is the height and width of the filter. We'll specify the stride, which says how much we move every time we shift the kernel over. Another important thing is padding. So we specify padding. Often we specify padding as same, which means apply whatever padding is necessary so that the output has the same height and width as the input. And we can either specify the activation function directly here, if we want it to come immediately after the convolution. Sometimes we want to apply other things first. So for example, sometimes we want to apply a convolution, then batch normalization, and only then apply the activation. So if we do that, we would use no activation function in the convolution layer, and then explicitly add an activation layer later. But for now, I'm not going to do that. So I have my convolutional layer with an activation inside the convolution layer. Then I have a pooling layer. So remember, a pooling layer downsamples. So it moves over the image. And let's say for each pool area. So here I'm going to look over a 2x2 area at a time. I'm going to apply some aggregation function over that, and that's going to be the output. So here I'm doing max pooling, which means I'm going to look over a 2x2 area of pixels, and I'm going to take the max pixel value in that area. Then I'll shift over and do the same. Okay. So you can see here, again, we have pooling layers available for 1D, 2D, or 3D, and we have max pooling available and average pooling available. Max pooling is kind of helpful for, detecting whether a particular filter was activated or not. So it's helpful for kind of picking out whether there's a bright pixel somewhere in the image or somewhere in the pool area. Average pooling has the effect of just smoothing out the image, but we'll see all that a little later. Okay, I'm going to follow that with a batch normalization, and then another convolutional layer, and then I will follow that with a global pooling. Global pooling applies pooling to just entire image at once. So if I have, let's say, 10 filters here in each layer, which, by the way, I don't need the same number of filters in every layer, but here I have that. So if I have 10 filters in each layer, the global average pooling will, let's say, take the average output of each of those 10 filters, and we'll create a vector of size 10, and we'll feed that to the output layer. The output layer is a dense layer, which is a fully connected layer. So we always end our convolutional network with a fully connected layer. And I'll use a sigmoid activation function because it's a binary classification problem. Okay. And again, I'll use binary cross entropy because binary classification. So here's our model. I'm going to go ahead and fit it. Let's see how it does. By the way, you might notice that it's still training, even though, I said to, let's say, stop if it isn't improving in a while. Even though the validation accuracy is not changing, the validation loss is changing. Remember, the loss is a cross entropy loss, binary cross entropy loss, which looks like this. Let's remind ourselves. So the binary cross entropy loss doesn't directly use a prediction like y hat. It uses zi, and we know zi is associated with the probability of belonging to a particular class. So you can have a situation where maybe all of the points are classified correctly, but let's say maybe there are some points where you say, okay, have a 60% probability of belonging to the positive class. So if you keep training, you become more and more confident in those predictions. Then you might say by the end of training, it has 99% probability belonging to the positive class. You can still reduce the loss function with it, which is a binary cross entropy, even though the accuracy is already perfect. So that's due to increasing the confidence of each prediction. There's a question in chat: do we have to specify the kernel for the model? I'm not sure what you mean by that. Do you mean, do we need to specify like the actual values in the filter? So we specify the size of the filter. So we said the filter is going to be a 3x3 filter. We don't specify, let's say, the weights of the filter. Those are learned. Okay, so here's the results. We can see the convolutional neural network did a lot better than any of our other models. What's very interesting about this is that the convolutional neural network, we know, is not looking at pixel-wise values. Instead, it's looking for some, kind of inherent forwardness or backness to each slash. It's kind of a better representation of what's already there. So it's actually much better, not only at training, at validating on this data set, but it can also do better with, let's say, slightly different data, but that still has, the same forwardness or backness in the slashes. So I'm going to generate another version of this data set, which has much heavier noise in the background and also longer slashes. Okay, so here was the original data set. You can see it has kind of light noise. The noise weight here is 0.5. And it has smaller slashes, they're about like 4 pixels each. And now I'm generating more noise, heavier noise. So the noise scale is 0.9, and the size of the slash is much bigger. And here's the predictions for this data set. So you can see that our convolutional model has perfect accuracy on this data set too, even though it's pretty different from the original data set on a pixel-wise level. And I could imagine, let's say, the k nearest neighbor model would not be able to do this well at all. But as long as each image still has the same like fundamental forwardness or backness about it, it does a good job. I can even change the rotation of the slashes. Let's try that. So now every slash, so previously they were exactly at 45-degree angles, either forward or backward. Now I'm going to randomly generate a rotation angle. And now you can see they're not all at the same rotation, right? So some of them are tilted more forward than others. Okay, let's see how it does. Okay, so you can see it still does a good job classifying these particular samples. Okay, perfect accuracy with up to, let's say, a 10 angle difference in the rotation. Let's try increasing the difference in the rotation angle. Okay, so now the rotation angle could be up to 30 degrees off the 45-degree angle. Let's see how it does. Okay. You can see it's still maybe a little less confident in some examples. Like here, it says this has a 96% chance of being a 1, where previously it was very confident it was a 1. It says this has a 4% chance of being a 1. It's actually 0. So it's a little less confident in the predictions, and the accuracy might be slightly less, right? But it's still 99% accurate at this data set with different angles and slashes. We can even make it even more extreme. Let's change our rotation angle to 40, right? Now, some of these are hardly even slashes. Some of them are practically vertical or horizontal lines. And it still actually does, not terribly. So this one, for example, that's practically a vertical line, is misclassified. Many of the others are actually classified correctly. And the overall accuracy on this new data set, where the angle might be as small as 5 degrees, is still 95%. Let's take a look at what this network learns. So we're going to go back to the original test data set, and we're going to look at the output of each layer. Okay, so remember we have a convolutional layer, a pooling layer, a batch normalization layer, another convolutional layer, and then a global average pooling layer, which does an average to make it fully connected again. All right, so let's pay attention to this. Okay, so this test sample is a backward leaning slash. And we notice that some of the filters seem to be activated by this and some are not. What do I mean by activated? So this is the output of each filter in the first convolutional layer. So I have 10 filters in the first convolutional layer. And they're each kind of going to be tuned to pick up on something different. And some of them are going to be activated by the forward slashes. Some of them are going to be activated by the backward slashes. Some might be activated by neither, and some might be activated by both. So which filters seem to be activated by the forward slash? Okay, so it looks like 2 and 9 are have been trained to pick up on, this is a backward slash. 2 and 9 seem to have been trained to kind of pick up on that, backward slash angle. 3 is a little interesting. Notice that there are like 2 lines. It looks like it's kind of picking up on, let's say, the top edge and the bottom edge. If you, let's say, move down the top of the image down. Let's look at maybe some other test samples that might belong to the other class and see if different filters are activated by the different classes. So the backward slash activated filters 2, 3, and 9. Here's a forward slash. Which filters are activated by the forward slash? Okay, so we can see 0, 4, 5, and 7 kind of pick up on that forward slash pattern. It looks like 8 is kind of analogous to what I think 3 was before, that it's picking up on both the top and bottom edge of the slash. That's why you have this double line. 1 looks like it's picking up on the space around the slash, so it's kind of picking up on the noise. And let's say it's picking up on all of the surrounding space to the slash. So let's compare that again. Backward leaning slash activates filters 2, 3, 9. Forward leaning slash doesn't really activate 2, 3, and 9 much. So just, a couple of random pixels. But some of the others are strongly activated. Let's see some other slashes. Okay, here's another backward leaning slash. Definitely activates 2, 3, and 9. Right. Okay, and a forward leaning slash, we can see 0, 4, 5, 7, 8 again. And that 1 thing. It looks like 8 is activated by both forward and backward leaning slashes. But you can see a very consistent pattern. So certain filters have been tuned by the training process to pick up on whatever makes a slash forward leaning, and some have been tuned by the training process to pick up on backward leaning slashes. Let's look at the next convolutional layer. Okay, so here's the forward leaning slash, activates these filters. Let's look at what the next layer does. So the next layer does max pooling. Okay, so we can definitely see the pattern here on the filters that were activated, like 0, 4, 5, and 7. Right? It's not as obvious in, let's say, the ones that are not activated. It's a little hard to see in the black and white, but these are actually just kind of like, black background, gray background with, let's say, a couple of random white pixels. Let's compare this to maybe some others. Right? So here we can see 0, 4, 5, very obviously activated. Where here we can see 2, 3, 9, very clearly activated. So the pooling layer kind of downsamples a lot. So we don't necessarily need to know every single pixel in the image. We just need to know this image, this filter was activated by this convolutional layer. Okay, the next layer is batch normalization, which just does some rescaling and centering. So it's not as relevant, at least visually. Right? So let's go back to the beginning a minute. Okay, we had this forward slash activates filter 0, 1, 4, 5, 7. Then we do some pooling. Again, we can see that activated those particular filters. Then normalization, which is scales and recenters. Then we have another convolutional layer. Now, in this other convolutional layers, we have 10 filters again, but each one scans over all of the 10 filters from the previous layer. Let's look at an example here, actually. So this is kind of a neat little demo that I just added last night, which kind of helps you see how layers learn from one another. So this is a model called Lynette. Let's see if we can get an image of its architecture. Okay, here is Lynette. I'm going to put it on top. Okay, so I'm going to write something in here. All right, so let's see what let's say more sophisticated network does. It takes the input, right? Here's the input map. So it's 32 by 32 by 1 input. That's this layer here. The next step is a convolution. In this demo, you can click on this little thing on the side to either collapse or expand a layer. So you can see the first convolutional layer produces a volume of size 28 by 28 by 6. That means if you click on it and expand it, right, it's 6 individual filters, each of size 28 by 28. And you could see from these lines, there's no connection between the 6 filters. Each one just scans the entire image. Okay, the next layer is a pooling layer. Right, so each pooling layer operates over one filter individually. So going back to our example here, we had a convolutional layer with 10 filters, and then a pooling layer which produces 10 outputs. So each of these 10 outputs corresponds to just one of the filters. Now the next layer is another convolutional layer. And this next convolutional layer, I can move this a little bit, you can see has 1, 2, 3, 4 by 4. So the next convolutional layer has 16 filters, so you can see that here. And each filter scans over all of the outputs from the previous layer. Right? So in our example, in our second convolutional layer, we have 10 filters again. Right? But each of those 10 filters scans all of the 10 outputs of the previous layer. So it's not a one-to-one correspondence. All right, so here we can see again, now these filters, again, don't have a one-to-one correspondence with the previous set of 10 filters, but they're very clearly looking for something specific in the output. Okay. So you can see very clearly here that this particular sample activates 0, 2, 3, 4, and 7 very strongly, whereas the other convolutional filters just see noise. So whatever features they're looking for in the output of the previous layers, not finding them. Let's look at some other test samples. Okay, so this one, 0, 2, 3, 4, and 7 are activated. This one, clearly 1, 5, 6, 8, and 9 are activated. So we can see that different filters are activated by the different classes because they're looking for different features in the image. And if we move on to the last layer, which is the output of our global average pooling layer, so we can see, okay, certain, let's say, last layer convolutional filters, if they're activated, are strongly associated with belonging to each class. So this example is a forward-leaning slash. We can see that the forward-leaning slash is strongly associated with having activated filters 0, 2, 3, 4, and 7 in the second and the last convolutional layer, right? 0, 2, 3, 4, and 7. Let's look at other samples. Okay, I can tell without even looking, this is a backward slash because this one activates 5, 6, 8, and 9. This one is again forward slash because it activates the exact filters that are trained to identify forward-leaning slash. And if you scroll over these test samples, you can see this very obvious pattern where some filters are clearly trained to learn the forward-leaning slashes, some are trained to learn the backward-leaning slashes. And that is why they do such a good job of identifying, even slashes with different rotations. We could even try here. Let's see what they learned for, let's see what they do for the slashes with different rotations. Let's see if this works. I might need to do some reshaping. Okay, so now I'm using the slashes with different rotations, right? So we still see that different filters are activated by forward-leaning slashes and backward-leaning slashes, right? Here I can see 0, 4, 7 activated by the forward-leaning slash, but not by whatever this is, which I think is a backward-leaning slash. This one seems to activate 5 and 9. Right, this one's clearly a forward-leaning slash. It activates 0 and 7. This is a more challenging data set, right? The network was not trained on this data set with different rotation angles and longer slashes. But the same filters that identify a small slash generalize well to a bigger slash. So that's why it still works so well even with a slightly different data set. Okay, any questions? All right, so we're going to look a little more at this on a more complicated data set now. We're going to look at a convolutional network trained on the handwritten digits data set. And this is more challenging to train. In terms of it takes longer to train. So I'm going to make sure I'm using a GPU on Colab to train this data. Colab allows you to have one GPU session at a time. So I need to terminate my other session. And now I'm able to connect to this one. Okay. So I'm importing this MNIST data using this MNIST load function, right? Which is a keras function that I imported here. So this imports the data still in its original shape. So I have 60,000 training samples. Each one is 28 by 28. And 10,000 test samples. Okay. I'm going to prepare the data by scaling it so that the output is in the range 0 to 1. And let's do that. And I'm also going to separate out some of the training data to use for validation during training. So for example, if I want to do early stopping, that's a type of model tuning. So if I'm doing early stopping, I need to make sure to pass a separate validation set and not the test data set to my model. Now I'm going to start with a fully connected neural network. Okay, so I'm going to feed it, let's say, where's my input? Okay, so my input shape is a dimension of the input data, which is going to be 784, right? Because I have 28 by 28 images. I have 512 hidden units in a single hidden layer. And then in my output layer, I have 10 outputs because this is a multi-class classification problem, 10 outputs using the softmax function. And in the hidden layers, I use a reload activation function. Okay, the activation function in the hidden layer is completely up to me. The number of hidden units is also completely up to me. The number of input units is defined by the problem. The number of output units is defined by the problem. And the activation function in the output layer is also defined by the problem. And of course, that has to match, right? So if I have 10 output units, I can't use a sigmoid activation. Sigmoid activation doesn't know what to do with, 10 output units. Okay, so here's my network. And I'm going to compile it. Again, I need to choose the appropriate loss function for my particular problem. So if I was using a regression problem, I would do, let's say, mean squared error. If I'm doing binary classification, I can do binary cross entropy. If I'm doing a multi-class classification, I still need to know whether you use categorical cross entropy or sparse categorical cross entropy. So let's take a look at the shape of the output data for a moment. The shape of the label data. Okay, so you can see there's just one output label for each sample. So for that kind of format, I would use a sparse categorical cross entropy. If my target variable was one hot encoded, so that let's say for 10 classes, there's a vector of length 10 label for each output, then I would use categorical cross entropy. Okay, let's train the network. I'm going to use early stopping again. So I'm going to say, if after 5 epochs, my validation accuracy has not increased, I'll stop. So you can see this stopped training pretty soon because the validation accuracy was not improving. I actually think this did not do a very good job. Right? It's only about 97%. Even the training accuracy is not that great. So I might choose to fit it a little more. So this is a training history. I think the early stopping was probably too aggressive here. So I'm going to train it some more. Now, when I train it some more, I just call fit again, and it will continue training the same network. But it's going to overwrite the previous history that I wrote to. Okay, so now it's stopped again. The training accuracy is still around 99%. The validation accuracy is around 97%. Okay, let's make some predictions. I have two ways to evaluate the model. I can either, let's say, generate the predictions and then compute the accuracy score for them, or I can use a built-in evaluate method on the model directly, and it will tell me the score. Okay, so the built-in evaluate model returns, the built-in evaluate method returns two values, a loss value and an accuracy value. And this model gets about 98%. So it's all right, but it's not great. If we look at some of the examples that are misclassified, some of them are difficult for humans, some of them are not so much, right? Like this 0 was predicted as an 8. I can tell it's a 0. This 7 was predicted as an 8 also. Some of these are pretty easy for humans, but the fully connected network did not do very well. I'm going to try to use my own test samples. So I have some digits here. Let's try one out. I'm going to use, say, the digit 7. I'm going to wait for that orange bar to go again. Okay, so here's my digit. I'm going to do a little processing to put it into the same format as the rest of the data. Okay, so I didn't do too well on this. It thought it was a 3, probably because there is writing in these particular pixels. So although the fully connected network did pretty well, it's still only doing a kind of pixel-wise learning. So it's easy to mistake things like this, a 7 and a 3, where it has writing in the same areas. Let's try something else. Let's try a 4. Okay, so I'm going to read in a new file, my 4. Okay, so this one, it got pretty well, right? So it's very confident that this is a 4. What do you think will happen if I try and put the 4 like off center like this? So I'm going to upload the same 4, but now it's not exactly centered very well. Okay, so now my 4 is off in the corner. Okay, now it's pretty sure that the 4 is a 0. Right? So the fully connected neural network did pretty well in some images, not so well in some others, especially if the image is not exactly centered. Let's move on to our convolutional network. Evan thinks our convolutional network will do a much better job with the non-centered images. I agree. But before we train our network, actually, I'm going to go ahead and start training the network because it takes a while. Actually, no, I'm not. Okay. So before we train the network, let's take a closer look at what convolution does. So I'm going to give an example of, let's say, a set of weights in a convolutional filter. So imagine we have this set of weights in a convolutional filter. Okay, it's a little difficult to see from the scale. Maybe I'll change the scale. Okay, here we go. So now it's a lot easier to see that the top row is positive values and the bottom row is negative values. Now, let's say I take an image of some random noise. Okay, so I'm randomly generating pixel values for every pixel in this image. Now, I'm going to do the convolution of this filter over this image. Okay, and to do the convolution by hand, I could use a SciPy function, correlate 2D. So this does our convolution operation. Okay, so the convolution of this filter over this image just found some noise. So you could think of it as, this filter would not be activated by this image. Now, what if I take the same filter and pass it over this image? Let's see what this filter does. This filter is positive in the top row, negative in the bottom row. So when you place this filter over an image, let's say place it over part of an image, it computes an approximation of the gradient, right? So an approximation of the change in intensity from the top row of the filter to the bottom row. So this actually acts as a horizontal edge detector. So you can see this detects horizontal edges. This part is very strongly activated. Similarly, you can rotate the same filter and make it a vertical filter. Right? Sorry, horizontal filter. It's showing the wrong one. Yeah, there's my vertical filter. Now, if I correlate this one over my image, right, you can see it detects those vertical edges. I'm going to go ahead and start training this network, and we'll come back to it in a moment, just because it takes a little bit of time to train. Okay, and while it's training, let's just make sure there's no problems. All right, while it's training, let's look a little more closely at that convolution. Okay, so let's say I take that horizontal edge detector, right? So here is the kernel. Now I'm going to move my mouse over the image over here. So this image shows pixel data. So there is large values, meaning let's say heavy writing across this diagonal and also in the corner here. And then small values in these, let's say, lighter blue regions of the image. Now, when I move my mouse over the pixel data, I'm effectively moving the kernel, right? So the filter over the image. Okay, and this section here will show me what part of the pixel data my kernel is over. This will show me kind of the result. So we know that to do the convolution, we do like an element-wise multiplication of each selection and the kernel weight. And then we add them all up. So this is the element-wise multiplication. And what it says here is, the result of adding them up. Okay, so let's say I put my kernel over here. Now this kernel tells me the change in the intensity of the image from the top row of the kernel to the bottom row of the kernel. So what's the change in intensity from the top row to the bottom row here? There is no change at all, right? So you can see when you do that convolution, right, you do that element-wise multiplication and you add it up, the change is 0. Now, what if I move my filter down here? So what's the change from the top row of the filter to the bottom row of the filter? Well, for the first two columns, there's no change at all, right? So you could see if you, let's say, add up the result in the result matrix, if you add up the first two columns, you get a 0. But in the third column, you could see there's a change in intensity of minus 99. Right? So here my filter is detecting a change in the intensity of the image in the horizontal direction. Okay, let's move the filter down one more. Okay. Now the filter actually just moves across the image like this, but I just want to show you this particular edge. Okay, if I move the filter down one more, let's look at what the change in intensity is. So in the first column, the change in intensity is there's none, right? So in the image, there's just ones all the way down. In the second column, the change in intensity from the top row to the bottom row is 99, right? Minus 99. And this particular kernel weights the middle column more heavily. So that counts as like a change in intensity of 2 times minus 99, so about 200. And then looking at the third column, the change in intensity from the top row to the bottom row is minus 149. So that's a total change in intensity from top row to bottom row of minus 347. So you can see that, let's say, if the pixels are similar in the top row of the filter to the bottom row, then the filter is not activated by that kind of area of the image. But if there is a dramatic change in pixel values from top to bottom, then the filter is strongly activated by that part of the image. Right? Looking here, for example, you could see in the top row of this kernel, all of the image pixels are 1. In the bottom row of this kernel, all of the image pixels are 255. That's a very large change in intensity. So that's what the horizontal filter does. And the vertical filter just does the same thing in the other direction. Right? So here you can see, okay, so there is no real change. Let's change it. Yeah, I'm not sure these are quite right. Okay, but as you move this over the image, you can see how it computes this change. Yeah, I'm not sure this is quite right. I think they mix them. Okay, so this is what these convolutional filters does. So the convolutional filters move over the image and look for different features of the image, except instead of defining these weights in advance, the weights are going to actually be learned by the training process. There's a question in chat, is the behavior of the filter itself learned between epochs, or does it learn new weights, which adjusts the behavior of the filter? The filter itself is just the weights, right? So the filter itself is just, we define the filter size in advance, but then what the filter actually does is completely determined by its weights. Okay, so let's go back and look at our convolutional neural network. So now I'm going to train a convolutional neural network on the same data. Previously, we looked at the flat version of the data, which is, let's say, every sample has 784 features. Now we need input volume. So every sample is 28 by 28 by 1. Okay. And we prepared a model with a sequence of layers. Each layer has a convolution, a batch normalization, and activation. Some layers also have some pooling in them. Okay. And we end with flattening that. So that just, let's say, takes the final layer's output and turns it into a long vector. And we connect that to a fully connected layer. So we end up with a couple of fully connected layers. We threw some dropout in there for good luck. And we end again with a dense output with the softmax activation. Okay, so let's see how this model does. So this model does somewhat better. You can see the validation accuracy is 99% after just a little bit of training. Okay. And these are some of the examples of samples that are misclassified. Some of them are samples that you can see are also really difficult for humans. Like, for example, this one is supposedly a 7, but the model predicts 1. I probably would have predicted a 1 too. Or let's say this one, for example, is actually a 5, but it's very easy to see how even a human might mistake it for a 3. So we're getting much closer to human level accuracy here, which is not perfect accuracy. Let's try our own test sample. Okay, so this was our off-center 4. Okay. So you can see our convolutional network is very confident that this is a 4. Compare that to our fully connected network, which felt pretty sure that the same exact sample was a 0. Just like before, let's look at the output of these convolutional layers. Now, this is a little more complicated because we have both more complicated data and also more layers. So we're going to look at the output of this models at each layer for this 2-digit. Okay, so here's the first set of filters. Let's see. Okay, some of the filters are clearly activated by horizontal edges, like this. Some filters seem to be activated by, edges at certain angles, like this one seems to be activated by this. Some filters might be activated by, let's see, just kind of the filled in part of the image, so not a particular edge, but just a positive space and negative space in the image. So different filters are probably activated by different aspects of the image. The next step is a batch normalization, which does some scaling, so it's not very visually evident. And then we apply an activation layer. Right? So here's what happens after the activation layer. After the activation layer becomes much more apparent what the filter did. So here you can much more clearly see that, let's say, this is activated by vertical edges, this by horizontal edges, this by the filled in space, and so on. Our next convolutional layer captures kind of more high-level details. So the lower level filters are more tuned to textures and edges. And as we get higher and higher in the layers, or farther and farther towards the output, now it's looking at combinations of those low-level features. So it becomes more difficult to interpret, but the actual features are more complicated too. So it's trying to capture some abstract concept of what it means to be a 2. So the next convolutional layer looks like this. And we apply, okay, so batch normalization is still not interesting. Okay, but here's the activation of that next convolutional layer. Okay. So again, we can see, some filters are strongly activated by different aspects of the image, while others are activated by other aspects of the image. And as we move higher and higher, okay, here's my pooling. It becomes more difficult to interpret what the filters are doing, but they're trying to capture like abstract concepts of 2-ness. Until eventually they'll come up with, some very long filter bank that will be fed into a dense, fully connected layer, and that will be turned into those softmax probabilities. Okay. Now, sometimes you have models that take a long time to train, and you might want to reuse the model later without having to retrain it again. This is very common when you're working on projects in this class. So Colab has a time limit. You can't train a model continuously on Colab for like 4 days. So if you have a model that takes a long time to train, you can, let's say, fit the model for a while, and you can save the model weights, let's say, after a few iterations. So you can use this model conv, let's say, just call the save function on the model. And then you can reload the model weights later. So that's actually a really useful feature. So how do you use this? I'm just going to go ahead and start training the next part because it takes a while. Okay, so how do you use this? Well, I'll tell you what the really common pattern is when students are working on projects. So when you're training a model, you can set up a model callback. Let's remind ourselves about the callbacks. A callback is something that runs after every epoch. Okay? So we saw, for example, early stopping can be a callback. We saw, for example, reduce the learning rate if there's a plateau is a callback. When you're training a model that takes a long time to train, a very common callback is to, let's say, save your model weights after every epoch. So you can save a checkpoint or the model weights to the disk. That way, if your training gets interrupted or you need to do something else or your Colab session is stopped, you save your model weights, and then you can always come back, restore the model from the last weights, and then you can just resume training whenever you feel like it. So you can train in little bursts. Now, there is one complication. The one complication is if you save your model weights directly in the Colab file system, then when your Colab session ends, your files are also gone. So the typical pattern is as follows. If you're working on a project and you have a model that takes a long time to train, first you'll mount your Google Drive. I'm going to show you how. So first you would mount your Google Drive in your Colab workspace. And I showed you how to do this in, let's say, the Colab tour from week 1. So you can find that, let's say, code snippet in here. Okay, so you mount your Google Drive. And then when you're setting up your model training, let's go back there a sec. Okay, so when you're setting up your model training, you'll add a callback for a model checkpoint. And you'll configure it to save the model weights in your Google Drive. So let's say after every epoch or every, let's say, number of epochs, so you can adjust the frequency, it will save the weights in your Google Drive. And you can always restore from those weights. So that means that anytime your training is interrupted, you can always just come back and continue training by restoring weights that are going to be saved in your Google Drive. Okay, let's look at one more way to improve the model performance with data augmentation. So with data augmentation, we supply more training samples by producing modified versions of the original training samples. So here I'm going to use the same network, but instead of training on the images directly, you could see I'm training on a train generator. Okay, and the train generator is created as follows. So first I define, let's say, an image data generator. And when I define an image data generator, I can specify what are all the things I want to do to that image. Okay. So here is my image data generator class. So I have a lot of choices of things I might want to do. So for example, I can shift the image along its width. I can rotate the image. I can shift it along its height. I can adjust its brightness. Right? And for each of these, I can supply a range. So for example, for one particular image, I might say, okay, in the image data generator, you can shift it up to 50% in each horizontal direction. So now suddenly that one image turns into many possible images. And you can specify exactly what type of transformations you want to allow. So you can do a width shift, height shift. You can change the brightness shift. You can shear it, so kind of twist it at an angle. You can zoom in or out. You can shift the channels, so let's say the red, green, and blue channels. You can flip it. You can scale it. Or you can apply some other predefined functions. So this is a really helpful thing for generating more versions of the data. And this helps in 2 ways. One, it prevents overfitting. You have more samples to train on. Also, it means that your model might be better at classifying, let's say, more difficult images just because it's seen more difficult images in training. Okay, in this particular case, it seems to have stopped training after not very good accuracy. So I would probably go back and train again. I think the early stopping was maybe a little too aggressive there. But let's see how it does on some of our more difficult samples. Okay, so these are some of the misclassified images. Again, this is pretty close to human level accuracy. Like looking at this line in the first example, I would probably have predicted a 4 too. Or similarly, this 0 and 7, it's very easy to see why it was misclassified, and a human might also misclassify it. Here's what it does at our own test sample. Now, sometimes you find that here you can see, for example, it's a little less confident that our own test sample is a 4. That's just because it's seen so many, let's say, malformed digits that now it can kind of understand that, like, yeah, sometimes 4s look like a 1. So it's probably seen examples of ones that really look sort of like the 4, and that's why it's a little less confident in the prediction. So the data augmentation can kind of help in a way, but you can see it can also hurt a little bit sometimes. Okay, we could try, let's say, another image. Let's try something a little crazy. Let's see what happens if I give it 2 images. Yeah, I don't know if it will be able to handle that, but we'll see. Obviously, it's still only going to give me 1 class, but let's see if it picks up on either of the actual true values. Okay, so my fully connected network is pretty sure it's a 0. My convolutional network actually kind of picked up on this vertical line, so it thinks it might be a 1 or a 7. All right, my data augmentation network is pretty sure it's a 1. Let's try another example. What should we try? I'm going to try, let's say, 3. But I'm also going to kind of scribble on my image a little bit. Let's see what our models do with this. Okay, so our fully connected network thought that was a 7. Convolutional network definitely picked up on the freeness. And so did the one that was trained on augmented data. Okay, any questions on this notebook? The last notebook we'll look at today is a transfer learning notebook. Now, this one takes longer to train, like about 10 minutes. I've pre-trained this notebook for you. Okay. And this one is going to apply transfer learning to a more difficult problem. So the handwritten digits problem we know is pretty easy. Even the classical machine learning models can get 90-something% accuracy on it. We're going to work with a more difficult data set, which is a rock, paper, scissors data set. So this is a series of images of hands making the rock, paper, or scissors motion over a white background. And you could see this is a much more challenging data set. There is a lot more variation in, let's say, how people make rock, paper, or scissors. Some of these are even difficult for a human to classify. Like, I might have thought this was scissors, not paper. We also have different skin tones and there are shadows. So it's definitely a more challenging data set. Okay, we'll pre-process the data set a little bit. I'm scaling the images. I'm resizing them to particular image size. So the reason I'm resizing them to this particular size is because I'm going to use a pre-trained model and apply transfer learning to learn this data set. And the pre-trained model expects a particular input size. So to use the pre-trained model, I need to first pre-process the data set by scaling my image to that expected input size. Okay, so here's examples after pre-processing. They look the same, just they've been scaled a little bit. And I can actually use this image format. This is like a tensor format. I could use it directly to train the model. But since we're more familiar with like NumPy arrays, I converted it to NumPy arrays first. Okay. I'm also uploading my own test sample. So this is my own version of scissors. And after I train the model and evaluate the model, I'm also going to try it on my own test sample. This is just a good way of kind of detecting whether the model generalizes, for example, to other test conditions, like my hand is not over exactly the same white background, and so on. Okay, let's try out our pre-trained model. So I have a list of pre-trained models available here from Keras. So here's a chart of some models. Now, how do I decide which model I want to use? Well, first of all of these models are scored on a data set called ImageNet. Okay. And I have two accuracy values for each of these models. I have a top 1 accuracy and a top 5 accuracy. Top 1 accuracy means what % of the time is the, let's say, is a model's prediction of the most likely class correct. So this is actually very difficult because ImageNet has a huge number of classes. I'm going to show you a list actually. Okay, so these are all the classes in ImageNet. You can see a lot of animal-related classes up here at the top. They're very specific classes, like different types of crabs, for example. So the top 1 accuracy means that the correct class was the one that the model predicted with the highest probability. So you can choose your model according to top 1 accuracy. The top 5 accuracy says what % of the time is a true class in one of the 5 classes that the model said is the 5 most likely. So this is like a slightly easier version. Now you might also choose models according to size and parameters. So some of these models have many more parameters or much more heavyweight than others. For this particular problem, I'm choosing a model called MobileNet, which you can see is much smaller than some of the others and also has fewer parameters. And it also has a smaller depth. MobileNet was specifically designed to run on mobile phones. So it's a very lightweight model. So that's the one I've decided to use here. Let's scroll back a little. Okay, so I've chosen MobileNet as my model for this example. It comes in a few different versions, and you have to choose which version you want. So the versions are, let's say, pre-trained for different input sizes. So when you, let's say, load the base model, you also specify the input size you want. You can't pick any input size you want. You have to choose one of the, the pre-trained models that are available. But you can find the list online that tells you what are the available sizes. Okay, so here's a MobileNet model. Right? You can see it's a much more complicated model than any of the ones we've used so far. So it has many layers. It has many parameters. So let's say sub-millions of parameters. Now, this model has, let's say, 1,000 potential classes at the output. So the output layer produces 1,000 outputs. Each output is a probability from 0 to 1 for each class on this list. So let's say, if the third output is a 0.1, that means that the model predicts that there's a 0.1 probability that this image is a goldfish. So what do you think will happen if I, let's say, apply this model to my test image? So this was my test image. What do you think this model will tell me if I, let's say, tell it to classify this image? So it's going to give me a probability for every single thing on this list. Now, some of the things on this list are animals, some of them are other stuff. Sorry, just plugging my laptop. It is very animal heavy, but it's not exclusively animals. But the point is that, let's see, rock, paper, and scissors are not choices on this list. Let's see if a hand is on this list. Hand is not on this list either, right? Maybe skin. Nope. Okay. So there are not really any relevant classes on this list of classes that it's been trained for. So let's see what it tells me the 5 most likely classes are for this image. Okay, so it tells me the most probable class is Band-Aid. Has about 90% probability of being a Band-Aid. The next most likely classes are thimble, rubber eraser, hammer, and drumstick. Okay, so it's not really close, but that's expected because this classifier was trained specifically to classify images in a particular data set, and all of the images in that data set belong to one of these 1,000 classes. So it doesn't really know what to do with a hand making a rock, paper, or scissors gesture. Right? So why is it helpful to me? Well, the reason it's helpful to me is because we know the convolutional network has, let's say, a series of convolutional layers that do feature extraction. And then the output of the feature extraction layers are fed to these fully connected layers. The fully connected layers learn some weights that are associated with class probability. So the model is not really helpful for me for this part, right? So we're not really interested in predicting the per class probability of any of the items on this list. But the feature extraction part is probably very useful, right? So the feature extraction part was trained on a huge number of images, and it's learned to detect some features that could potentially be helpful for me in any general image classification task. So here's what I'm going to do next. I'm going to get the model again, but this time when I'm going to download the model, I'm going to say, only give me the base layers. Don't give me the classification head. This part at the end is called the classification head. And then I'm going to add my own classification head on top. So my classification head is going to be different. It's going to have 3 output units because I'm trying to predict between 3 different classes. So here I'm going to get the base model again. And when I download the base model, I'm going to say include top equals false. That means don't give me the fully connected layer at the top of the network. I also need to specify what it should do then, with the output. So I'm going to say pool it using the average method. Okay, so here you can see at the end, the last layer, there's a convolutional network, a convolutional layer with a batch normalization and ReLU after it. And then a pooling layer that's used to transition from, let's say, convolutional to fully connected layers. But there is no fully connected layer at the end for classification. So I have this base layer here with many pre-trained convolutional layers. This is saved in base model. Now I'm going to make a new model. Okay, so it's going to be a new sequential model, just like the ones I've done before. But instead of adding individual layers to the sequential model, I'm going to say add the entire base model. So all of these layers with their pre-trained weights. Then I'm going to add a dropout layer, and then I'm going to add my own classification head. Okay, so my own fully connected layer with 3 units and a softmax function. Now, notice that before I added the base model to the new model, I also set trainable to be false for the base model. So now all of the base model parameters, all of the weights in the base model that are part of MobileNet are frozen, which means that when I train my new model, it's not going to update those weights. It's only going to update the weights in this last part, my new classification head. So it's going to take the already learned feature extractor, and then I'm going to train my new classification head to take those extracted features and predict the probability of belonging to rock, paper, or scissors classes. Okay, so we compile the model. I'm going to use some data augmentation to train the model because, it's a complicated data set, always helpful. Okay, and let's see what happens. So when you start off, you can see that the model accuracy is around 30%. So it's about the same as random chance, right? So early on, it's not really effective at all at, let's say, taking those extracted features and mapping those to rock, paper, or scissors classes. But you can see that as I continue to train the model, it gets better. So after 20 epochs, it has about 90% validation accuracy on the rock, paper, scissors task. Now, this is fine. I might even continue training it longer just like that, and it might continue to do better. But we also said that sometimes if the new classification task is very different from the previous one, well, the lower convolutional layers, so the early layers that learn like extremely local details like textures and lines and edges, those are really very generic. They don't depend on the specific task. But the higher layer convolutional layers, so the filters in the layers closer to the output, they learn features like abstract features that are more specific to the particular class. So if the task that I'm trying to do now, so the rock, paper, scissors task, is different from the task on which the model was trained, which is an ImageNet task, then I might want to not only train the classification head, but also update the weights in the, let's say, higher convolutional layers. So this is a typical approach we follow. We need to do that. First, we train just the classification head with a relatively high learning rate. So here I use the learning rate of 0.001. So I train the classification head only with a higher learning rate to kind of get it in the right place, so get it pretty close. And then I'm going to fine tune the later convolutional layers. So fine tuning the later convolutional layers means, okay, now I'm going to make the base model trainable again. So I'm going to unfreeze it, but I'm going to then refreeze just the first layers of it. Okay, so let's say I said, okay, freeze the first 149 layers, but the later layers on the base model are going to be trainable. And I'm going to train those at a much smaller learning rate because I don't want to make like big dramatic changes here. The features learned by the higher layers are still useful. I just want to tune them a little bit to the particular task. So I'm going to use a much smaller learning rate here. Now you can tell that I've unfrozen some layers by looking at the trainable parameters when you look at the model summary. So in the first time when I trained my own classification head, in the model summary, it told me I had 3,000 trainable parameters and about 2 million non-trainable parameters. Now when I'm fine tuning the model, I'm going to allow the later feature extraction layers to also be trained. So I have about 700,000 trainable parameters and only 1.5 million non-trainable parameters. Okay, so now I'm going to call fit again. Remember, when I call model.fit, it doesn't make a new model. And notice that I didn't define a new model here. So I'm not defining a new, model equals. I'm just modifying the existing model. Okay. So when I call model fit again, I'm just going to pick up where I left off training. Now it's very common for the accuracy to drop a little at first, like the validation accuracy to drop a little at first after I unfreeze those layers, but hopefully it will kind of get back up again. Okay, in this case, it did not. So I would probably expect to have to train it a little bit longer. Okay, you can see here the training accuracy went up. The validation accuracy is still not so great. So I'd probably train this one a little bit longer. Okay. And you can see the training progress over time. So this is the part where I trained just the classification head. And this is a part where I trained, I fine-tuned the later layers too. Let's see how it does on my own sample. So you see it was pretty good at predicting the class in my own sample, which was scissors. Okay, so transfer learning is really powerful because it gives you some built-in feature extractors. Now, I want to emphasize that it's really helpful not only as a feature extractor, but it also kind of expands the knowledge of your model. What do I mean by that? So here's a cool example. This is a game called AI Dungeon. Okay. So this AI Dungeon is a game in the style of like classic text-based adventure games. Has anyone ever played this game? Okay. So Adventure is one of the earliest computer games. It's an entirely text-based game. And it's basically like a choose your own adventure type scenario. So you're given your state in the game, and then you have to give commands to say what you want to do next. Okay. So here, for example, I'm standing at the end of the road. Around me is a forest. I can say, go north. Okay. And then I move around the game by typing commands. Now, this game was implemented, if we go back to sign in. I don't remember how to sign in. Let's see. Right. Okay. So if we go back to this drawing we did on Tuesday. So this game was implemented as a classical rule-based system. If you look at the source code of this game, which is publicly available, it's a series of go-to statements. So there's a limited set of inputs it accepts. And for every combination of inputs, it defines exactly what should happen next. Now, AI Dungeon is a game in a similar model, but AI Dungeon is a machine learning version of the game. And here's how it's trained. So to train AI Dungeon, let's actually play a version of the game. Let's pick what we want to play. Okay, I'm going to play this version of the game. Okay. So AI Dungeon is a machine learning version of the game. It accepts any type of input, so not only specific commands. And the output is generated by a machine learning model. Let's wait for it to start my world for me. Okay, while it's starting the world, I'm going to tell you about how the model was trained. So to generate a training set for this model, they scraped a bunch of games from, let's say, this website called chooseyourstory.com, which is a series of story games where, let's say, it has text that's written by, people who contribute these games for the public. And you can choose an action after each text, and it shows you what happens next. Okay. So this was a data set used to train the game. But they didn't train the game only on this data set. So they started with a GPT-2 model. So this is a model trained on a data set of 8 million web pages. Okay. And then they only fine-tuned it using the data they scraped from here. So what does that do? Well, it means that the model actually has the knowledge of those 8 million web pages. But then it kind of presents it in the style of these stories. Let's go back to our world. Okay, it's still creating our world. Let's choose a different one. Hopefully this is faster. Okay, if it's not faster, I'm just going to tell you what to expect. So what's interesting about this is, okay, so it presents still like a kind of interactive interface where you can type commands. But when you talk to the game, you can actually tell it about like anything in current events or politics or history or science. And if what you're talking to the game about was in that, set of 8 million web pages, then the model actually has some knowledge of whatever you're talking to it about. So fine-tuning the model is really powerful because, well, not only does it extract good features, but it also expands kind of the universe that your model understands and knows about. Okay, it looks like it's not going to allow me to Let's see, not going to allow me to start a world here, but let me see if I have some screenshots of old versions of the game to show you what I'm referring to. Okay, I don't seem to have any. Well, anyways, it's 10:30. We're going to stop here. Are there any questions today? All right, very good. I will see you all next week.